Hello GATE aspirants, welcome to part 2 of GATE solid state physics series. Question number 8. The temperature T dependence of magnetic susceptibility chi of a ferromagnetic substance with a Curie temperature Tc is given by. Now for ferromagnetic material, chi is equal to C upon T minus Tc when temperature is greater than Curie temperature. So here option B is correct. So this susceptibility will depend on temperature only when temperature is greater than Curie temperature. Below it, the susceptibility is almost constant and it will not depend on temperature. Question number 9. The order of magnitude of the energy gap of a typical superconductor. This energy gap is roughly, it is 10 to the power minus 4 electron volt. So we can see it is of the order of 1 milli electron volt. So here option D is correct. Question number 23. For a three-dimensional crystal having n primitive unit cells with a basis of p atoms, the number of optical branches is. Now for a unit cell which has p atoms, so a unit cell containing p atoms per basis, the number of optical branches is, or let me write first acoustic branches. So number of acoustic branches is 3 and possible ways are 3p. So number of optical branches is equal to 3p minus this number of acoustic branches, that is 3. So this will be 3 in bracket p minus 1. So here option C is correct. Question number 44. A metal with body-centered cubic BCC structure shows the first, that is smallest angle diffraction peak at a Bragg's angle of theta is equal to 30 degree. The wavelength of X-ray used is 2.1 angstrom. The volume of the primitive unit cell of the metal is. Now we know Bragg's law is 2d sin theta is equal to n lambda. So here 2 into d into sin 30 and n is 1 into 2.1 angstrom. So sin 30 is 1 by 2, so this will cancel out. So you will get d is equal to 2.1 angstrom. That will be value of d. Now d is interstellar spacing and it is equal to a upon under root h square plus k square by l square for a cubic structure. So here it is body centered cubic structure. So from here we can write 2.1 angstrom is equal to a, and we need values of HKL for this. Now we know first possible case is 100, next possible case is 110, next possible case is 111 and so on. These are possible cases. And for BCC structure, this is the condition, H plus K plus L, this has to be even. Only then we can get diffraction peaks for BCC structure. So here this is 1 plus 0 plus 0, that is 1, so this is not possible. 1 plus 1 plus 0 is 2, so this is possible. So the first diffraction peak will be obtained for this 110. So we will have 1 square plus 1 square plus 0 square. So this will be a by root 2. So a is equal to root 2 into 2.1 angstrom. That will be value of a. And if you want value of volume, then volume is equal to a cube. So this will be cube of this. So that is 2.1 root 2 cube, and this will be angstrom raised to 3. And this comes out to be 26.13 angstrom cube. So this is for BCC, but we know that in a BCC structure, the total number of atoms or in that state it will be 2, because we have this structure here 1, 2, 3, 4, 5 and 6, 7. So 8 such atoms are there on the corners. So effective number n will be equal to 1 by 8 into 8, and plus there is one more atom at the center, so plus 1, so this will be 2. So effective number of atoms in the BCC structure, it will be 2 per basis. So this volume is for n is equal to 2, and we want to find primitive volume. So for that we have to divide this by 2. So this will be V by 2. So that will be 26.13 angstrom cube by 2. So this is 13.09. So roughly we can say it is 13.1 angstrom cube. So this will be the answer. Next question. The tight binding energy dispersion EK relation for electrons in a one-dimensional array of atoms having lattice constant A and total length L is E is equal to E0 minus beta minus 2 gamma cos Ka, where E0, beta and gamma are constants and K is a wave vector. The density of states including spin degeneracy in the band is. Now density of states, we know that gk dk in k space, it is equal to L by pi for 1d case. So for 1d case this is the case, and here we have to consider spin degeneracy as well. So we have to multiply this by 2. So this will be L by 2 pi into 2 for 1d case. And if you want energy density, then we have to divide by dE. So this will be 2 into L by pi, and that will be, here I can write this dE by dk. So this will be energy density. So for that purpose we need to differentiate E with respect to k. So let us differentiate it. So dE by dk is equal to d by dk of E. So E0 is constant, beta is constant. So that will be minus 2 gamma cos, that is sin Ka, and into k, and this minus will become plus into A, because we are differentiating with respect to A. So d will be this, and then energy density will be 2 into L by pi into 1 upon 2a gamma, and then we have here sin Ka. So this 2 and 2 will cancel out. So this will be L upon pi a gamma sin Ka. This will be value of energy density. So L upon pi a gamma sin Ka. So option A is correct. Next question. Same data is given for this question as well. The effective mass of electrons in the band is. Now effective mass m star is equal to h cross square upon d2e by dk square. So this is the formula for it. We have to differentiate it 2 times. So dE by dk is, already we have obtained this value, 2 gamma a sin Ka. Then we are going to differentiate it again. Sin will be cos Ka, and one more a will come into picture. So 2 gamma a square, and that will be d2e by dk square. So m star will be h cut square upon 2 gamma a square cos K. So this will be the answer, and option B is correct. So these were all the questions from GATE 2011 paper. If you like this video, please give it a thumbs up and subscribe to my channel for more videos. Keep learning.